Okay, so what we have introduced previously, this psi of x, we said it is a wave function, a single particle wave function, but we landed into a trouble of having both positive and negative energy solutions, as well as there popped up another kind of particle. Okay, we had actually two particles in the theory, particle and antiparticle. Clear? Okay, so we then discarded this, interpretation for this psi. So now we will consider this psi to be a field. So then this equation will turn out to be the field equation for Dirac field, and we will call this psi as a field, or corresponding to the spin half particle. Clear? Got it? And we will okay. So this is also called as a Sittler field, because it's okay. What are how many components are there? There are 4 components in this psi. Okay, 2 components corresponding to a particle and 2 corresponding to an antiparticle. Clear? So, and this equation, the minimum possible dimensions we have already explored. It is 4. Clear? Okay, so it's a 4-dimensional equation, rather a 4x4 matrix equation in a space what we call as a Sittler space. Okay, because this is having 4 components, and gamma mu is the minimum dimension is 4. Okay. Okay. So let's construct the Lagrangian, which will give us the field equation for this spin. Okay, for this field psi. Okay, so we'll write the Lagrangian like this way. Okay, so the first thing what we need to consider when we try to have a theory, you first try to construct its Lagrangian. Okay, the way we have constructed for the scalar field, then complex scalar field. Clear? Here I will. Okay, so it should give you ultimately the field equation, the correct field equation. Okay, so let me write this as psi of x like this way. Partial mu and psi of x. Okay, so I will assume only this much. So let me take this as the Lagrangian density, or simply Lagrangian. Okay, from which we can construct the field equation. Clear? Okay, here psi and psi bar. Okay, psi bar, if you remember, this is defined through you are having psi dagger and this gamma naught. Clear? Okay, so and you are having this algebra, Clifford algebra. So gamma mu, so this is equal to twice G mu nu and an identity matrix, because this okay. So these are this identity is in the Sittler space. Okay, in a space where these gammas are defined, not in the Minkowski space. This G is defined in the Minkowski space. Clear? Got it? So this is a 4x4 matrix. Okay. So if you look at this Lagrangian, you can construct now the equation corresponding to this thing. So let's put it in the Sittler notation, this Lagrangian. Okay, so one more point, if you see this Lagrangian, it is not Hermitian. Okay, if you see, it is not Hermitian. Take it as dagger, you will see it's not Hermitian. Okay, so the Hamiltonian what you can construct it, that will not turn out to be the Hermitian, is it? But that is not true. You can construct a Hermitian Hamiltonian from here as well. How? You just add actually one term, that is actually a total derivative term, that will make this Lagrangian to be Hermitian. That I am not going to do here. You can do it yourselves. Which term you require to have this total Lagrangian to be Hermitian. Clear? So that does not. Okay. So that term is ultimately, you will see, that's actually a total derivative, and total derivatives vanish at boundaries. Clear? Got my point? Okay, so this suffices our discussion. I mean, this is the only important part of the Lagrangian which is required. Clear? Okay. So let's rewrite it. So I can rewrite it in this notation like this thing. So since this is a matrix, clear? If you see, it is actually a 4. Okay, so it is a 4. Okay, so this is a 4-column vector and this is a 4-row vector. Clear? So this is a column vector and this is a row vector, and this is a 4x4 matrix. Clear? So let me introduce those matrix indices. So let me write like this thing: alpha I gamma mu partial mu minus m. Let me write alpha beta here, psi beta. Clear? So this is a matrix now in terms of the matrix elements. Clear? Okay. One more point. Okay, so these indices we call, okay, the Sipner indices, these matrix indices, clear? Because these are the okay, so this will give me alpha the component of the psi bar, and this will give me the beta the component of psi. Okay, so got it. So we will call these alpha, alpha, beta, and beta to be as Sipner indices. Okay, so I can rewrite it like this way. Okay, so why this is important? Whenever you feel an ambiguity, okay, put the Sipner notation. Put everything in terms of the matrix elements. Okay, then do the calculations, then it becomes easier. Okay, so I can write it as psi alpha. Okay, so this is a derivative, it has nothing to do with the Sipner indices. Sipner indices will come on this gamma, so you are having this I gamma mu, okay, alpha beta partial mu minus, since this m is multiplied by identity, clear? So it will be simply m delta alpha beta, okay, psi beta. Clear? Okay. So now let's write the equation. I mean Euler-Lagrange equation. Okay. So let's calculate the conjugate momentum corresponding to psi. Okay. So let's calculate. So you are having. So let's calculate first conjugate momentum. Okay. So one more point, this psi and psi bar, these are two independent fields. You treat them independent, clear? The way we have treated phi and phi dagger in complex scalar field to be independent, similarly you put it here what? Independent, okay? So therefore, there will be two, okay, so if I am having a field psi, corresponding to this I can define the conjugate momentum. Similarly, if I am having field psi bar, I can define conjugate momentum, clear? Okay, so how I define? So let's define psi, okay? Conjugate momentum corresponding to psi, so it is partial L by partial 0 psi bar, sorry psi. So what is that? Partial L by partial psi dot. Like this thing. Clear? So now let's calculate it. So I need to figure out psi dot, okay?
Yes, sir.
So let's write it. Okay. So let's write it. Okay, so let's look at this very Lagrangian. Okay, so I can write it as psi bar. Okay, so I will forget x for the timing. It is I gamma 0 partial 0. Okay, there is a psi as well. Okay, then minus I gamma. Sorry, let's write I. So it is gamma I partial and psi minus m. Okay. Minus m psi by psi. Clear? So let's take this very Lagrangian. So where is your psi dot? Here. Clear? Okay. So therefore, I will write this partial psi. So it is the difference. So this will not give you anything. This will not give you anything. Okay. So this is only thing which contains psi dot. So what you will get? Now tell me. So you will get simply I psi. It is I psi dagger gamma 0 gamma 0. So it's I psi dagger. Clear? Got it? Okay, now since there is an asymmetry between, in this Lagrangian I have taken only the derivative on psi, is it? No derivative on psi bar. Okay? That's why I will be able to figure out from this Lagrangian only the conjugate momentum corresponding to psi. Now if you put the Hermitian, if you make this Hermitian, you will be able to figure out what? Psi bar. So that is simply actually minus I psi. Okay? So in that case, so I'll be having also, so that is minus I psi. Okay? So that means the psi dagger is actually the conjugate momentum corresponding to psi, and psi is actually the conjugate momentum corresponding to the psi dagger. Okay? Okay, so let's calculate the equations of motion. Okay. Okay. So what are the Euler equations? So you are having partial mu, partial L by partial mu some psi is equal to partial L by partial psi. So let's write it as alpha. Alpha means what? It's the Sipner index. Clear? Got it? Or you can put some another index. Let's put some Sipner index alpha, beta, gamma. Okay? So can anybody calculate this thing? Just tell me. Okay, so similarly you will be having an equation corresponding to, okay, like this thing. Since you are having two fields, partial L by partial mu psi bar, let's say gamma is equal to partial L by partial psi bar gamma. Clear? So let's take this rectangle. Let's take this object. Okay, so let's take this partial L by partial psi bar gamma. So what is your Lagrangian? Which contains, okay, so your Lagrangian is, okay, so this term contains derivative, is it? Okay, so this contains derivative, so it will not contribute to this. Okay, so this contains only psi bar, so it's like this thing, minus m delta alpha beta, okay, partial by partial psi bar gamma, okay, psi bar alpha, psi beta. Okay, so this is only the psi bar. Okay, so it will be minus m delta alpha beta. Okay, so differentiate it, so it will be delta alpha gamma. So then you are having psi beta. Okay, got it? Okay, so what this is? Minus m delta beta gamma psi beta. Because this will be non-zero only for when alpha is equal to beta or alpha is equal to gamma. Clear? So now let's take the another term. So that partial, okay, partial L by partial mu psi bar gamma. So where is this thing? Okay, so this is a derivative on which term? So have I done correct things? Sorry. This term will also contribute because there is no derivative on psi bar. I am taking this equation. Okay, so this equation will yield me an equation of motion for psi, and this equation will yield me an equation of motion for psi bar. Clear? I will try to figure out the equation of motion for psi. Okay, so now if I take partial L by partial psi bar, you are having psi bar out of derivative. Clear? So this term will also contribute, this will also contribute. Got it? So what you will get? So it will be simply partial by partial psi bar gamma. I'm sorry. So it is something psi bar alpha I gamma mu alpha beta partial mu psi minus m delta alpha beta psi bar alpha psi beta. Clear? So what you get? So it is simply, so when you differentiate, it will be simply, okay, like this thing, delta alpha gamma I gamma mu alpha beta partial mu psi. A differentiation of this thing. When alpha is equal to gamma, it is non-zero. When alpha is not equal to gamma, it is zero. Simply psi bar, that's one. Minus m and delta alpha beta psi bar, so it is delta alpha gamma psi beta. Okay, so this is non-zero. Okay, when alpha is equal to gamma, so you put alpha equal to gamma, so it is like this, gamma mu, okay, gamma beta partial mu psi minus m delta beta gamma psi beta. Clear? Got it? Everybody followed it? Okay, so now if I take this very term, partial L by, okay, so also you are having partial L by partial mu psi bar gamma, so this is equal to 0 because there is no derivative term on psi bar in this very Lagrangian. There is no derivative on psi bar. Okay, so this term will yield me 0. So now let's club the two terms. So there is an index on this side, beta. So it is beta. Okay, so therefore we get this object I gamma mu. Okay, gamma beta partial mu psi beta minus m delta beta gamma psi beta is equal to 0. Okay, so this you can write as like this thing, I gamma mu partial mu minus m. Okay, this way gamma beta psi beta. Can you write it? Simply you put the gamma beta index outside. Okay, so what this is, or you can simply have I gamma mu partial mu minus m acting on psi, that's equal to 0. So you got your Dirac equation back. Okay, got it? Any question? So that means the Lagrangian what we have written, it yields the correct equation. Okay. Okay, so if you put a differentiation with respect to, let's say, psi bar or psi. Okay, so if you make a differentiation with respect to psi, okay, so let's take this very equation. You will get okay, so let's take this one. So this equation yields you what? The usual Dirac equation, what you know. So if I take this thing, so it will give me actually an equation for psi bar. Okay, so let's take it. Let's take this partial L by partial psi gamma. So just tell me what are having. Let's take partial psi. Okay, so which term contains psi gamma? So this contains, but it is within the derivative. Okay, so you are having this objective. So it is minus m partial by partial psi gamma. Okay, psi bar alpha psi beta. So what you will write, minus m psi bar alpha delta alpha beta. Okay, so sorry, so it is delta alpha beta here. Okay, so it will be delta beta here. Clear? So from the second term, you look, delta alpha will be replaced by simply gamma. Okay, so now let's take partial L by partial mu psi gamma. So how much is that? So you are having that term, the first term. So psi bar alpha, okay, psi bar alpha will come out, I will also come out. Then you are having this gamma mu alpha beta, it will come out. So then you are having this thing, partial by partial mu psi gamma. Okay, acting on this partial mu psi beta. Okay, so I should have put some different factor here. Okay, so let's write it as a new, and let's write this as new, because this mu is a dummy variable here. It's a dummy index. Okay, so what is that equal to? So it is psi bar L. Dirac equation again. So you are having, this is the Dirac equation, I gamma mu partial mu minus m psi, that's equal to 0. Clear? So let's take its dagger. Let's make its conjugate. Okay, take its dagger. Okay. So I am taking now dagger of this. What will happen? This psi will go on this side. So you will be having psi dagger. Then you are having, so I will go as minus I. Then you are having gamma mu dagger partial mu minus m, that's equal to 0. Clear? Okay. So now let's write it. So I'll write gamma psi dagger. So I'll multiply here gamma naught square, because gamma naught is equal to 1. Okay, so this is equal to identity here. Okay, so you are having minus I gamma mu dagger partial mu minus m, that's equal to 0. So what it yields me? Psi. Okay, so this objective, okay, these two, so it forms psi bar. Okay, psi bar is what? Psi dagger
gamma naught. You multiply this through, so it is minus I gamma naught gamma mu dagger, okay, partial mu minus m, that's equal to 0. Yes, there is gamma naught. Okay, so now let's multiply on left by gamma naught. Okay, so multiply here what? On this side gamma naught. Okay, so what you will get? So this gamma naught becomes, so it is gamma naught gamma mu dagger gamma naught partial mu minus m gamma naught square. So that's equal to 0. So this is equal to 1. Can you tell me what this object is? So we are having this gamma mu dagger is equal to gamma naught gamma mu gamma naught, which implies simply this gamma mu is equal to gamma naught gamma. Okay, so this is simply gamma mu. So you are having psi bar. Okay, now tell me on where this derivative acts. So I should have put that. So this derivative acts on this side psi, clear? So because it is the partial mu psi, so you are taking its conjugated. So this is acting on this side dagger. So you put an arrow on like this. So it is okay. You take an minus out. It's simply I gamma mu partial mu plus m. That's equal to 0. It is the conjugate Dirac equation. Huh? Okay. Okay. So let's. Okay, so let's take the Fourier decomposition of this very field. Okay, before that we'll impose a quantization condition. Huh? So now you are having, okay, so you are having this psi of x. What is its conjugate? Psi dagger, clear? So we will write its conjugate in terms of psi bar, clear? So this is the equal time commutation, sorry, anti-commutation. Psi bar y p. Okay, so we'll use the anti-commutation. Can anyone tell me? I delta x minus, and all other anti-commutators are 0. So we are quantizing. So for I will tell you. Okay, we'll take one more lecture. So because you need to understand why this has to be anti-commutator. Okay. Look here. So in case of bosons, we imposed a commutation relation, equal time commutation relation, which defines the quantization rule. Okay, and for fermions, okay, for Dirac particles, we impose, or for fermions in general, we impose an anti-commutation relation. Clear? So why this is to be so? Because it has to be inconsistent with the principle of causality. Okay. So what it means, so if you remember the first day lecture, I told you there, so there is when you are having a wave packet moving, so if you look at what is the probability of finding the particle in the space-like regions, so it is finite if we are having a single particle wave function solutions. Clear? So that means it violates the causality. Clear? You are having a space-like region where you can figure out there is a finite probability, and it has not to be there. Okay, so this is an inconsistency. How you resolve it? One should try to quantize the field. Okay, so the quantization yields you the no probability of finding the particle within the space-like regions. Clear? You got my point? So this kind of paradox is resolved by the quantization. Now how it resolves? For bosons, you impose the commutation relation and that very problem is resolved. But for fermions, if you impose, let's say, the bosonic commutation, so it is not resolving any kind of problem. It yields you and one more point, we are having the negative energy problem. Okay, so the quantization resolves the negative energy problem. Okay, so if I impose, let's say, the bosonic commutation rule here for the quantization, so it still has then the negative energy problem and this causality violation. Clear? So these two problems exist there. But if I impose then the anti-commutation rule, okay, so my problem is both the problems are resolved. Okay, and it is well defined within the spin statistics relation. Okay, so you have to, because for fermions you are having what? Fermi Dirac statistics. Clear? So the wave function is antisymmetric in nature, and for bosons the wave function is symmetric in nature. So it is actually consistent with the quantization rule. Okay? Okay. So let's impose for the time being this thing, then I will go deeper into it. Okay? So for if I impose this kind of permutation, so I need to figure out what is the Fourier decomposition of the field. Okay? So since I am having two particles at hand, one particle and antiparticle, it is the same kind of decomposition what we have done for the complex scalar field. Okay, for complex scalar field we have identified the phi represent in terms of the annihilation operator of the particle and creation of operator for the antiparticle. Clear? Similarly, you are having the same thing here. Two particles are represented by the theory, one particle and another antiparticle. So we expect two operators in the Fourier extension. Okay, so let's, in light of these, let's write the Fourier extension of this very psi field. So let me write this psi of x. So it is simply the plane wave expansion like this thing. Okay, so let me write first let me write this very factor e raised power minus I p dot x. Okay, then I will write okay as sigma since okay, so let me write u s of p. It represents, it is a sigma corresponding to the particles because I am having a spin structure here. Clear? So us is actually a 4-column vector. So you are having, okay, so if I take, let's say, only the electron, so this us will be like this thing, only 1 0 and 0 1. Clear? So if you are having a particle at rest, okay, so this is a sigma corresponding to an electron, but it will be in general. Here you are having a 4-component formalism. In the 4 components, it will be actually a 4-column vector. So let's say you will be having 1 0 0. Let's assume 1 0 0. Clear? Or 0 1 0. And similarly, okay. So you can think this 1 0 0. So I mean this will represent a particle, and there will be actually the another sigma which will represent an antiparticle. Clear? Okay. So these come because so these are actually the solutions of the Dirac equation. Okay, free particle solution of the Dirac equation. And I will write now, instead of, we are having the A operator, is it? An annihilation operator corresponding to a particle. Clear? For that, I will write an annihilation operator corresponding to a fermion. Okay, why I am putting S? S means a spin. Okay, so how many possible spins are there? 2 possible spins, spin up and spin down for a particle. Okay, so that means for each spin you will be having a plane wave. Clear? So it will move as a plane wave. So that's why now I will put a summation over that S. Clear? So this will represent simply the annihilation operator for a particle with spin S, and this is it a sigma. Okay, so it is simply the sigma representation. Okay, and this is your plane wave. Clear? Okay, so then I will write then another operator. Let's write the antiparticle. So I will put this antiparticle in terms of the tilde. Okay, so it will be actually now the dagger. So FSP, because it is the creation operator. Okay, then I will write this BSP e raised power I p dot x. Okay, so let me write what are the equations. They satisfy this Vs and this Us. So we have this equation. Okay, so I gamma mu partial mu minus m acting on psi, that's equal to 0. Clear? Although I have shown this thing Us and Vs when we are doing the solutions of the Dirac equation. Clear? So, but let me tell you this way. So you are having this object. Clear? So now act this partial mu. So this is equal to 0. Partial mu will act on this EP. Clear? So it will bring me down minus IP. So minus I and this it will become plus. So gamma mu P mu minus M acting on this U. Got it? So what you are having? So this will imply that you are having gamma mu P mu. Okay. minus m acting on u s of p will be one equation, because by this condition this is equal to 0, then this has to be equal to 0. Similarly, that will give you, okay, minus gamma mu p mu minus m v s of p is equal to 0. So in other words, I can write these equations like this in p slash minus m, okay, u s p is equal to 0. Here I will write it as p slash plus m acting on v s p. So now you can see these are actually the solutions of the Dirac equation, okay, plane wave solutions. Got it? Okay. Now similarly, okay, since you have written psi, therefore I can write this psi bar of x. Psi bar means actually dagger, clear? So what will be that? So it is simply d3p by root of 2 pi cube, okay, twice e. So by the way, these are the three momentas. And you are having summation over s. So I will now write this f dagger. So you will be having now f dagger s of p. So it will be the creation operator of the particle. Then since you are having the bar here, psi bar, you will put a bar here, us bar. What is us bar? So this is simply u dagger and gamma naught. Okay? E raised to, so you are having now it as a plus I p dot x plus f tilde s p v bar s of p e raised to minus I dot x. So here, yes? Any question? Problem?
एक्चुअली कैमरा थोड़ा बोर्ड कॉर्नर नहीं आ रहा था, इसलिए मैं इसे दोनों से चेक कर रहा था.
Clear? Any question? So now let's write the total Hamiltonian. So these are important. Okay. So let me keep these things here. So let's write the Hamiltonian. Now, how I write the Hamiltonian? So h is equal to integral d3x, this Hamiltonian density. Clear? So what is that equal to? So it is d3x. Okay. Then I will impose, okay, after writing the Hamiltonian, okay, then I will impose the condition on this f and f tilde. The quantization rule, what we have figured out. So I will use those. You will see why I need to impose it. Okay. So I will write in a moment. So what this will be? So you are having pi. So pi corresponding to psi, and you are having psi dot here, right? Minus that one. Okay, clear? So what you are having this object d3 of x. What is pi psi? It is I psi dagger probably. Clear? Then you are having this psi dagger, psi dot minus L. What is L? What is L? Okay, so you are having, so that what was L? Psi bar I gamma mu partial mu psi minus m psi bar. Okay, so let's write it. So it will be, anybody? So it is psi bar. Let's put it in the, so I gamma 0 partial 0 psi plus I psi bar gamma I partial psi minus m psi bar. So how much is that equal to? So this is equal to psi. Okay, so this will be I simply psi dagger, because gamma naught and gamma naught equal to 1. So you are having this psi dot here. So it will be minus, because gamma I, in this partial I, it will be simply like this thing. Yes? Any question? Any question? Huh? So it will be psi dagger gamma naught okay, gamma dot p, okay, okay, I have taken inside, acting on this minus m, okay, side gamma dot side, okay. So now use it here. So you are having I. So have I done anything wrong? So plus side dagger gamma naught gamma dot p, okay, side plus m side dagger gamma naught side. Okay, so this term cancels with this thing. Okay, so what you are having? So you are having simply d3 of x. So side dagger gamma naught. Okay, so you are, so there should be an I here. There is an I here. No, there is not. Okay, so if I write an I here, so it will be simply like this thing, nebula. Gamma dot nebula. Huh? Okay. So it is minus I gamma dot nebula. So let me put it this way. So then, I need to, what is the sign? Is it correct sign? Sorry, it is plus. Okay, it's okay. So, so this, if you see, this is actually Dirac Hamiltonian. Is it? Alpha dot p minus plus m, beta m, right? And because you are having gamma naught here, so it is gamma naught. So gamma into, so gamma naught into gamma, that's actually alpha, if you remember. So it's alpha dot p plus beta m. Is this the Dirac Hamiltonian? So we started with it. Is that true? Okay, so now we have to use psi. Okay, so we have to use the form of psi and psi bar, okay, to figure it out. Clear? Got it? Okay, so let's first work out this very object. Okay, now look here, what I will do. Everybody carefully. So you are having this object acting on psi. Clear? So it means this is object. When you put psi, so it will be acting on this thing, us. Clear? So much it will not act on this f. It will only act on which? This us and e raised power minus ipx, because it is so you are having this derivative. Derivative will act on this thing. Clear? So and it will also act on this thing. So first let's calculate what is its effect on this part. Okay, so let's try to calculate it. Okay. So let's take this minus I gamma dot nebula plus m. So let's look at its effect on USP e raised power minus I p dot x. Clear? So how much is that? So this delta will act on this thing. It will bring as minus I p down. Clear? So it is like this thing. So let me write minus I gamma dot nebula plus m. Okay, e raised power minus I. So it is ept minus p dot x. Okay, USP. Clear? Because this is a 4 vector here, and this is a 3 derivative. Okay. So when this will act on this thing, you are having plus I. So minus I gamma dot IP, okay, plus M. Okay. So what you are having? E raised power. So USP e raised power minus I p dot x. Clear? So what that is equal to? Now tell me. So it is simply gamma dot p plus m acting on USP e raised power minus I p dot x. Okay, so now let's take this equation. You are having p slash minus m acting on USP, that's equal to 0. Okay, so we are having this equation. So it means what is that? P slash. So it is simply, so let me write gamma mu to save the steps. P mu like this thing. Okay, so what that gives me? So it gives me gamma 0, p 0, then anybody?
Minus gamma I P
Huh?
minus
Yes, minus
gamma
gamma dot p minus m
US
acting on USP, so that's equal to 0. Okay, so that's equal to, so I will be having now this gamma dot p, okay, plus m acting on USP, so that is simply equal to this gamma naught p naught, okay, p naught acting on USP. Can you tell me what is p naught? P naught is simply EP. By quantization rule, all these momentas are not independent, okay, only 3 are independent, okay. So that is simply equal to gamma naught EP US, where EP is the energy of the particle. So therefore, okay, so therefore you are having this object to be equal to, so this will be simply equal to gamma naught EP USP. So keep the order of these things. Gamma naught is here and US is here. Okay? So because you are having gamma naught here, then US. If this is a matrix, this is also a column vector. Okay. So put your hand
it is
minus I dot x. Okay, so this will be the home assignment now. This objective show that. So if you are having now minus I, so let me write it here. So you are having this as home assignment, minus I gamma dot nebula plus m acting on VSP. So what it should give me? Anybody? So it is something minus times it is minus gamma naught EP VSP e raised for I p dot x. Okay,
yes, sir.
got it? So now we have identified what these things are. Okay, just substitute there. Okay, let's substitute. Okay, so let me write it here. So therefore I can write this Hamiltonian h is equal to integral dt of x, this side gamma naught. Okay, so minus I. So since this contains, okay, so let me write it this way, integral d3p divided by root of 2 pi q, okay, twice ep, then sum over s, you are having this fs of p, okay, clear? Then you are having this operator, this object, minus I gamma dot nebula plus m acting on USP. I have just put a step for you people, minus I p dot x. Then you are having this f tilde dagger s of p, okay, minus I gamma dot nebula like DSP e raised for I p dot x. Clear? And you know what is the value. Clear? For these things you know the value. So you are having d3 of x. Now let me, since this is psi bar, so this is simply psi bar. Okay, so I will put the form of psi bar now. So let me put the form of psi bar. So that's, let me write as d3p prime divided by root of 2 pi cube, okay, twice ep prime summation over s prime. So what is that equal to? So it is f dagger s prime p prime, okay, then u bar s prime p prime e raised by I p prime dot x plus f bar f tilde s prime p prime, okay, v bar s prime p prime e raised by minus I p prime dot x, okay, then you are having this return. Clear? So then you are having this integral d3p, okay, divided by root of 2 pi q twice ep summation over s, okay. Then you are having this fs of p, okay. So what this object is? It is gamma naught, okay, gamma naught ep, okay, usp e raised to minus ip dot s. Then you are having minus f tilde sp, okay, it is dagger. Then you are having this object as gamma naught ep vsp e raised to ip dot x. Okay, clear? Just I have substituted the values. So now you have to do the space integration. Integration over x. This we have been doing all the time. Okay? So let's do the space integration. Okay, so the first thing, so there is a normalization condition. Okay, since this u and v signals, they are orthonormal to each other. Clear? So it is something like this. So let me write. So if you are having, okay, so it is, let's write u dagger v, that is equal to 0, and v dagger u, that's equal to 0. Clear? So this means, so if I am having u bar, then gamma naught v, that's equal to 0, because u bar is u dagger gamma naught.
Yes.
So gamma naught square is 1. So this means v bar gamma naught u, that's equal to 0. Okay. So but the momentum argument should be same. Okay, at least. So now if I do, can you do the space integration? Okay, so let me take this very term. Okay, so let's take the first cross term, then I will take the direct term. Let's take this term and the last term. Look at the first. So what is the exponential? So let's take the first and last term. So you are having this as 1, this as 2, let's say this as 3, okay, this as 4. So let's take 1 and, okay, 1 and 4th term. So what you are having? So that's equal to d3 of x. Okay, forget about these p integrations, forget them. Okay, so forget about these f's as well. What you are having? Okay, so let me write it as.
US prime.
So let me write all the terms. Sorry. So you are having d3 of x, this f dagger s prime p prime, u bar s prime p prime. Okay, for this exponential, it is a number, so forget it. So what you are having there? So f tilde dagger, is it sp? Clear? Then you are having this gamma naught ep and vsp. Clear? And then you are having this exponential e raised to I p prime plus p dot x. Okay? So that means, okay, so there is an integration over this d3p and d3p prime and divide by that root. Okay? So let's take this integration. This depends on x. Clear? So what it yield me? So if I make now the integration over d3 of x e raised to I, that I can write as ep prime plus ept, okay, minus I p plus p prime dot of x. So that will be simply, so this will yield me a delta function. Clear? So it will be something 2 pi cube, okay, delta 3 p plus p prime, okay. And then you are having this exponential e raised to I ep prime plus ep. So this forces p to be minus p, because ep is root of p square plus m square. So p square and p prime square will be same. So that is simply equal to 2 pi cube, okay, delta 3 p plus p prime, okay, e raised to twice I ep t. Clear? Okay. So now let's integrate over this p prime. Okay, so what you will be having? P prime will be replaced by minus p. Clear? So what you are having? If you look, you are having those conditions. So you are having these. Okay, so you are having u bar, okay, then you are having gamma naught, then you are having v. So what you will get?
0.
Okay, got it? Samajh aaya?
Yes, sir.
So by that very condition, the off diagonal terms will be 0. What remains only? These terms 1, 3 and 2, 4. Clear? Samajh aaya? Okay. So if you do it in the same way, just okay. So if you look here, so what you are having integration over x, e raised for I p prime, p prime minus p. So it will simply be delta 3 p minus p prime. Clear? So you will be having e raised for I ep prime minus ep. So ep prime will be same as ep. So exponential will not come. Clear? Samajh aaya?
Yes, sir.
Okay. So shall I write the result? So because we have been doing all these things. Okay. So let me write. So the non-zero terms will be like this thing. So therefore this h is equal to integral d3p divided by 2 okay summation over s prime. Okay. Yes, so why there is no 2EP? So EP, you are having EP here, okay? So they will cancel out. So it is root of root, so it will be simply EP. Those will cancel out. That's why here is 2. So you are having this F dagger S prime P F S P like this thing. Then U dagger S prime P U S P, okay, minus okay F tilde S prime P F tilde dagger S P, okay, V dagger S prime P V S, okay. So now there is an okay. So you are having these objects. So the normalization. This is simply the normalization condition of U signals and the V signals. Clear? Okay. So we are almost done. Huh? Just so the normalization condition is this U dagger, okay, SP USP. So that's 2EP delta SS prime. So that is same as V dagger S prime P VS P. Okay, just this is a home assignment. Just show it. It is simple. Figure out the solutions of the Dirac equation in terms of U signals and multiply them in this way. You will get this as the normalization condition. Clear? Okay, just use it there. So what you get? Okay, so therefore you will get this h is equal to, so you are having this twice EP delta S sum over S prime, so S prime will be replaced by S, okay, so EP, so it is integral d3p, okay, and then you are having 2 will cancel, so you are having simply EP like this thing, summation over S, then you are having F dagger SP, okay, FSP, okay, minus F tilde SP, F tilde dagger S prime. Clear? So now what F dagger F will represent, since it is a F dagger is the creation operator of the particle, so it will give me the number operator. Okay, so here comes the point what I was saying. So if I normal order, say okay, so look here. So this is in terms of the number operator, the way we did for the which case, bosonic case. Okay, if I normal order in the usual way, such that commutation relation vanishes. Okay, if I normal order, okay, let's say normal order in bosonic way. Okay, so what does that mean? So it means, so I have to put annihilation towards the creation of this thing. So it means, so this is already normal order, this objective. So what you are having here, if I normal order this thing, So I'll be doing like this thing. If I do the bosonic way means, so it is not prime, it's S. So it's like this thing. If I normal order it in this way, so what I mean by that, so you put like this thing. Just put the annihilation towards the creation operator. Clear? How it is done? Such that this commutation is such that you have imposed actually this these are F tilde S of P. So this commutation vanishes. Okay? So normal order of this thing vanishes. That means I have imposed actually a commutation relation, is it? So now let's use this F dagger here. So that means I am putting this here. So what it comes with then? A negative sign. So that means if this term is large, so you will be having a negative energy there as well. So negative energy is not resolved, the problem of negative energy. Now how to resolve it? I have to normal order the fermion in such a way such that the anti-commutation vanishes. Clear? Okay, so you put, okay, so normal order in such a way that anti-commutation vanishes. So that means I have to do the normal ordering of these operator S of P. So F tilde S of P. So that's equal to minus F tilde S of P F S of P. So what I have assumed here, okay, so what is the condition I have imposed? So that's actually the anti-commutation rule. So those are actually the quantization condition. So the quantization condition what I have used here is that this F S of P, okay, F S prime P prime, so it is dagger, so that's equal to delta S S prime delta P P prime, and similarly, okay, so it is momentum is a continuous variable, okay, and F S P, okay, F S prime P prime, so it is equal to delta S S prime delta P minus P. Clear? And all others are 0. And all other anti-commutators are 0. So therefore I can write the normal ordered Hamiltonian. So this finishes off. So normal ordered Hamiltonian this way. So it will be simply D3P EP. So you are having now the summation over S because both spin states will contribute. So you are having F dagger SP FSP plus F tilde dagger SP, okay, F tilde SP. Clear? So that means the energy is contributed by both ends of the particle. Okay? Got it?